Hello and welcome back. We are finished with finding the solutions for first-order differential equations and its applications to natural physical systems and designed systems. Starting today, we are going to solve for the solution of higher-order differential equations. But to set the context for this course, we are going to only focus on linear ordinary differential equations, second order, and beyond. So, why linear? And are there nonlinear ODEs? Yes, of course there are. Pero mo focus lang ta sa linear not only because those are the most commonly occurring differential equations that could model real-world systems, but also because nonlinear ordinary differential equations will be for us, at least for us engineering in the engineering field, are more of a trivial kind. That's why we are going to only focus on solving for the solutions of linear ordinary differential equations. So let's start. An nth-order linear ODE has the following form. The first-order linear ODE, nga to na-encounter before, could also fit this format, where the coefficients b of x and function g of x are all functions of x and of x alone. So, kanang tanan b of x nga coefficients of all our derivative y to the nth prime and also g of x should be just functions of x alone. We have also known that if g of x is equal to 0, our ODE or our linear ODE is homogeneous, and if not, it is not homogeneous. Now let's focus again to our general form. If we divide the whole equation by the first coefficient of the nth order derivative, bn of x, so ato i-divide ni tanan by bx of n, bx of n, such that bx of n over bx of n is of course equal to 1, and g of x would be divided also by bn of x. It could be written in the form of L of y is equal to that equation in the middle part. L of y is equal to y to the nth prime plus so on and so forth, which also would be equal to, if homogeneous, 0, and if non-homogeneous, L of y would be equal to, or this whole equation, L of y would be equal to phi of x, where phi is equal to g of x over b n of x. If all of the coefficients are constants, the linear ODE could be called or has constant coefficients, and if not, it has variable coefficients. An nth order linear homogeneous ODE always has n number of linearly independent solutions. So kung unsang order sa ODE, maupod to ang number of linearly independent solutions. Now, what do we mean by linearly independent solutions? Consider our solution y of x is equal to c1y1 of x plus c2y2 of x plus so on and so forth cnyn of x. Let's say, for example, we have a third order linear homogeneous ODE. So, tungod kay third order siya, napuntay tulo or 3 linearly independent solutions. So, in this case, they are c1y1 of x, c2y2 of x, and c3y3 of x. What we mean by linearly independent is that each of them individually are in themselves solutions already to our differential equation. So, if si c1y1 of x lang, solution na siya daan. Okay? So, if sum siya sa c1y1 of x and c2y2 of x, solution po to sila duha together sa atong third order differential equation. And of course, C1y1 of x plus C2y2 of x plus C3y3 of x, katos lang tulo i-add, of course, solution sad yun to siya, no? Sa atong third order differential equation. So if fourth order, so napo tayo upat ka sets of linearly independent solutions, and so on and so forth. So for every y of x, those represent our solution, and for every c, those are our arbitrary constants. Now, how do we know if these sets of solutions are linearly independent? So we have a condition nga ato i-check for that. The solution is what we call the Wronskian, and that would be explained on the next slide. The Wronskian is W, the determinant, such that when it is non-zero, it is used to determine if the sets of functions z1 to z of n are linearly independent. So if natay sets of functions of an nth order differential equation, supposing those are our probable solutions to our ODE, linear ODE, ato i-subject og Wronskian. And if ang mugawas nga value is non-zero, then we just have proved na linearly independent ang katunga sets of differential, linearly independent to nga mga solutions sa atong differential equation. Now, how will we perform this? Quite honestly, it is easier than it looks. Okay, medyo intimidating lang ang atong notation, pero sayo na siya. Okay, let's say for example, we have a second order differential equation. No? Second order. So, with that, tungod kay second order siya, it follows na natay duha ka sets of probably linearly independent solutions. Let's note those as Z1 and Z2. Okay, so Z1 and Z2 lang. Next na nga step is, ibutang nato sila sa isa ka matrix nga format. And tungod kay duha sa kabuok, our matrix will be a 2 by 2 na matrix. So, si Z1 and Z2 only. Then, atong subject og first derivative, si Z1 and Z2. So, we have Z1 prime and Z2 prime. So, nanasa silang upat nga elements sa matrix. And then, we'll just perform determinant solution, no? Atong pangitawon ang determinant sa katunga matrix. And mao na to siya technically ang pagpangita sa Wronskian. The Wronskian would be the determinant of that 2 by 2 matrix. So if 3 by 3, we have Z1, Z2, Z3, atong pangitawon ang first derivative ni Z1, Z2, Z3. That would be our second row. Okay, second row. And then, ato na po pangitaon ang second derivative ni Z1, Z2, Z3. Moto ato ibutang sa third row. So, 3 by 3 matrix man siya kay naman tayo third order ODE. So, sa first row will be our Z1, Z2, Z3. Sa second row, ang first derivative ato nila and ang sa third row ang second derivative na ato nila. So, naatay 3 by 3 nga matrix nga pangitaon nato ang determinant. So, sa 3 by 3 matrix, maybe I'll just post a separate video on how to find the determinants of a n by n matrix. No? So, dapat square matrix siya. So, that's it. No? That's how we determine if a set of functions are linearly independent by solving for the Wronskian or the determinant of those sets of functions. So, mao to ang para sa homogeneous linear ODE. So, how about for the non-homogeneous? An nth order linear non-homogeneous ODE has the general solution. Y is equal to y of h plus y of p. Where y of h is, ako lang una state, y of h is the homogeneous or complementary solution to our linear homogeneous ODE. So, if natay linear ODE, first is, even if non-homogeneous siya, ato sa pangitaon ng solution sa homogeneous nga linear ODE. And the solution would be our y of h. And after finding or determining the y of h, we could also determine the y of p. So, muna siya ang general solution to our linear non-homogeneous ordinary differential equation. Okay? So, we have two general methods on how to obtain the general solution for our linear non-homogeneous ODE. We have the method of undetermined coefficients and method of variation of parameters, both of which we will be discussing next meeting. Okay?